Hello and welcome to the wee video on specific latent heat. So as I said earlier in the week, it's going to be a little recap because we have gone through this before, but we're going to go over what specific latent heat is and how to use the equation for it. So the equation we have for specific latent heat is that EH equals mL. Okay, E, that's our heat energy. We know it's heat energy because of a little h. M, as always, is our mass. And L is the new thing that we learned just for this. Okay, L is what we call the latent heat. Now, if we remember back to when we did this, and when we were looking at specific heat capacities and things, different materials will have different latent heats. These will always be given to you, okay? It'll either be on your data sheet, or it'll be in the question you're asked about. But what we need to remember is that each material will have two latent heats, okay? It will have a latent heat of fusion, and it will have a latent heat of vaporization. And we need to know the difference between these because we'll only get the right answer if we use the correct number. Okay? So, latent heat, this is the energy used when a substance is changing state. Okay? So when it's changing from a solid to a liquid or a gas to a liquid or anything like that, okay? It's the energy used to make that change, okay? And while that change is happening, remember, it doesn't change temperature of the substance, okay? So when ice gets to 0 degrees and it starts to melt, all the time it's melting and the energy has been used to turn it into liquid, it hasn't changed temperature. It stays at 0 degrees and all of that energy is used to change its state. None of it goes into heating it up, okay? And that's where these come in, okay? We use the specific heat of fusion when something is going between solid and liquid. Oh, I cannot fit that in. Sorry. Okay. So if something is freezing, we use fusion because it's going from liquid to solid. If something is melting, we use fusion because it's going from solid to liquid. Okay? And then it follows on from that. Vaporization is our other one. I'm going to write this way, okay? Just to fit it in. Vaporization is when we are going between liquid and gas. And again, it doesn't matter about the direction we're going in. We use the latent heat of vaporization if something is going from a liquid to a gas, but we also use it if something is going from a gas to a liquid and condensing. Just have to make sure we use the right one. So what we're going to do is, since we've done some work on this before, do a couple of word examples, then I'll get you to try some yourself. Okay? So our first worked example. Right, so our first example is how much energy is used to change 3 kilograms of ice to water at 0 degrees Celsius. Okay, so here we're going from solid ice to liquid water, so that means we're using fusion. Okay, now you'll find this on your data sheet, but the latent heat of fusion is 3.34 times 10 to the power of 5 joules per kilogram. So we'll do this just like we do every question. Write down what we have and what we're trying to find out. We also know the mass. The mass is 3 kilograms. And we're trying to work out the energy. How much energy is used. Okay? We have everything we need to put into this equation. We don't even need to rearrange it because we're trying to find out the energy. And it's already like that. So let's pop that down. EH equals mL. We've got a mark there already. No bother. Then we just substitute in. We know our mass is 3. And then we know our latent heat is 3.34 times 10 to the 5. Put this on our calculators, making sure we do this right. If you can't remember how to do scientific notation on your calculator, let me know, because it is something we need to be very comfortable with. Okay? When we type that into our calculator, we get 100,2000, and that's in joules. Now, we don't want to just leave it like this, okay? We want to put it to 3 significant figures, is normally what we do rounding wise in physics. So if we do this to 3 significant figures, the third figure is a 0, and because this next number is lower than 5, the 0 will stay as it is. And then every other number becomes a 0 as well. So there we're looking at an answer of 1 million joules, okay? Or if we wanted to be fancy, 1 megajoule, okay? Either of those is fine, just make sure you do your rounding to 3 significant figures, sorry. Now, that was a fairly easy example of this. We didn't have to rearrange the equation and everything was given to us. We could get a slightly trickier example, okay? So I've written this on a different piece of paper. I'm going to try and zoom in so we can see it properly. Okay, now this question is saying, if we used 400,000 joules to turn water to steam at 100 degrees Celsius, how much water would we be changing? So what mass of water could we change with that much energy? Next part is, if we were using a heater that was 500 watts, how long would this take? Okay, so if we were using a kettle to boil this water, kettle was 500 watts, how long would it take to do it? Okay, so let's tackle A first. Okay, write down what we have. We have an energy, EH equals 400,000 joules. Okay, how much water? So we're trying to find the mass. We don't know that, okay, but we do know L. And now we have to think about, is this fusion or vaporization? Okay, well, it's going from a liquid to a gas. So liquid to gas is vaporization. Okay, and again, you'll find this on your data sheet, but the latent heat of vaporization for water, remember it's different for every substance, is 22.6 times 10 to the power of 5 joules per kilogram. Now, let's write down an equation. EH equals ml, but we're going to need to rearrange this, okay, because we're trying to find out m. So we could put these in a triangle with EH at the top and then m and L. We're trying to find out m, cover it up, that gives us energy over the latent heat, so it means mass equals the energy divided by the latent heat. And then we substitute in what we have. So my energy, that will be 400,000 joules. And my latent heat, that will be 22.6 times 10 to the 5. Again, making sure we type this in correctly on our calculator. That should give us an answer of 0.17699 kilograms. Okay, so we're looking at less than a kilogram there. But again, it's a bit too many digits. We want 3 significant figures. So the first 0 doesn't count. We start counting from the first non-zero number. So that's 1, 2, 3. The third significant figure is a 6. We look to the number next to it. Since that's higher than 5, it means the 6 is going to pop up. So it's going to be 0.177, and everything else after it becomes 0. So you don't need to bother writing these 2 zeros after it, because we don't do that. So with that much energy, we can only turn 177 grams of water to steam. Okay, not a lot. Then the next bit is to work out how long that would take. So for part B, we're trying to find out a time. We know an energy, that's been told to us. An energy is 400,000. And we've also been told a power. Remember, watts measures power. So what we have to do now is see if we can remember any equations or look through your datasheet that involve these three terms, okay? Now this equation we've seen in the electricity topic, but it does come up here in the energy one as well, because it deals with energies. And so that equation is energy equals power times time. And we have all these things, but again, we're going to have to rearrange it. So if you need to use your triangle, we'll have energy at the top, then power times time. Cover up a t, because that's what we're trying to find. So then that leaves us with energy divided by power. So the time equals the energy divided by the power. Sub in 400,000, 500. Pop this in your calculator and you get an answer of 800 seconds. So it's taken quite a long time to do this change as well. Okay, so that's a trickier example. We had to do rearranging in both parts, and then we had to use what we knew about heat and combine that with another equation we first learned in the electricity topic and put them together to work something out. Okay, but there was nothing new here. These are both equations we should be familiar with by now and happy rearranging. Okay, so hopefully that was a good reminder of what we covered before on latent heat, and now you'll be able to go away and try some questions yourselves. Okay, so thanks for listening.